Hello, my name's Alan. Good afternoon. I'm here with Ahmed, and we're going to talk a little bit about the OAM design challenges and some recommendations we have moving forward. This is the OAM, or OCP Accelerator module that we've been hearing a lot about this afternoon. It's really a designed for some of the AI workloads, machine learning, deep learning applications that are rapidly evolving. As you can see, it's a modular form factor. And what that allows is for different vendors such as NVIDIA, AMD, Intel, Habana to come up with hardware that's interchangeable, that's serviceable, and it's modular. And we heard a lot about that during this afternoon as well, the idea of this spec being modular to allow different vendors to participate, to produce hardware very quickly for the marketplace and for our customers. And that's very key for this spec. Physically, it's 165 millimeters by 102 millimeters. And Song mentioned that the size is increasing a little bit in OAM 2.0. But generally, this is the form factor. The SoC is on top with both a stiffener on top and bottom and two mezzanine connectors. And as you can see in the top, there's a UBB that's 5 millimeters, the difference, the height, Z height between the OAM module and the UBB connector. Here, this is, you can see what I want to talk a little bit about here is the areas that we can place the VR components. And this is where, it's challenging for PD engineers to provide power for this module. There are four main areas, top and bottom, or north and south. This is where we typically put our controllers and some of the input power on both sides, as now power is being delivered from both mezzanine connectors. And on the side is where we place our other VR components close to the SoC to reduce IR drop, right? Now, if you look at the dimensions where we can actually place these components on the top and bottom is 20.5 millimeters. Do I have a, oh, there you go. Yeah, 20.5 millimeters by roughly 70 millimeters on the north and south. And then on the side, we have approximately 80 millimeters between the mezzanine connectors. And from the X, we have about, let me see here, it's about 30 millimeters. So you can see from the areas that we actually have, it's not a lot. And the components are very tight, packed in around the SoC. Some of the design challenges that we have with this particular module, the keep out zone limits I've talked about already in the previous slide. We're very limited in the four areas that are given for the power. Thermal limits is also very challenging for this module. It's expected to work in very stringent environments. The W4, it's a 45 degrees C inlet temperature spec, and that really poses a challenge to how much power can be delivered to the SoC. And we're talking about 700 watts, 1 kilowatts. So the thermal limits really poses a challenge for the PD and for power delivery. We also heard a lot about SerDes and PAM4, and all of that, the high-speed I/O we're using the same PCB space that the VR components and the VR is using. So we're sharing the same space, and that's a challenge. That's really hard for the PDN. So what that means is we're having to use smaller components, higher switching frequencies, and routability is hard for this particular module. We have SoCs that have many rails. So for the PDE engineer, now on this limited space, now we have to route all these rails to the SoC. So that again is a challenge for anybody designing PD, right, for this module. And lastly, the environment, the input power range for this module, for these servers, are anywhere from 40 volts to 59.5 volts. And what that means, it really affects the efficiency and the overall performance of the power delivery. So all these things pose different challenges for this module, for the PD, and that's something that's it makes it very, very difficult for us to work. Now, let me talk about some of the design challenges that we have. I talked on the previous slide, I already mentioned some of the kind of physical challenges. For the longest time now, buck technology has served us well. It's served us well in the CPU world for decades. It's served us well in the PCIe add-in card space, and that's been worked very well for those form factors. But for this particular form factor, I think the buck has hit its limitation, and we really need to think about that. Current density as well for the PD space industry hasn't kept up with the SoC. The power density keeps increasing year over year, every 2 years, right? According to Moore's law, the power density increases, but the PD hasn't kept up, the PD industry. And this is something that needs to be addressed, right? Because of the areas that I talked about before, we've had to go to higher switching frequencies to get smaller components, and everybody's okay with that, except as we go to higher switching frequencies, our switching losses also increase. So practically, there is a limit to how high we can switch on the PD solution. Magnetics is bulky, so we go to higher switching frequencies to get smaller components, but even with that, the magnetics is oftentimes the biggest component when it comes to X, Y, and Z height on the PD solution for these modules. So that's a challenge that we need to overcome to get these parts smaller, right? Thermal resistance, again, is key. We're talking about 1 kilowatt modules, 1 kilowatt. The thermal resistance of power stages that are anywhere from 2 watts to 4 watts per degree C is simply too high. And we need to look at other solutions because we can't cool these components. So that means we've had to add more phases to reduce the current per phase. But then again, we bump into the area that we have, and you can only put so many phases down before you ran out of space. And lastly, the PD industry has relied on the CPU ecosystem too much, and the parts are not optimized for this form factor, right? The topology, the components, everything is just, it's not working optimally for OAM modules, and we need to look at a different way, right, for the PD industry to move forward. And next, I will hand it off to Ahmed.
Okay. Thank you, Alan. Thank you, Alan. Good afternoon, everyone. Okay, now we have 2 messages to deliver a recommendation point of view. One message for our friends in the power community and research community. Other message would like to deliver it for the facility, the data center facility or facilities. Okay, as Alan mentioned, it's time to look for a new topology. We are delivering in a very tiny card, 1 kilowatt. It's not only the power density is high, but also the processor is going lower nodes. The voltage is going from 0.6 to 0.5 to 0.4, and it's going to keep going down. So imagine with the voltage going down and power going up, imagine how much current we need to deliver in the same card. And the development cycle is very, very fast. We have to deliver a new card with a new power almost every 2 quarters or 3 quarters because the demand is going up and up. Thank you for Meta. So we need to look for now a scalable topology. Buck has been used for a long time, and yes, the ecosystem is available, but the time is look for a different topology. Why not we start looking for a direct conversion topology, taking 48 directly to 1 volt or sub 1 volt. Ecosystem is available for buck, ecosystem available for two-phase because it's working for the CPU motherboard, but for the OAM, we need to look holistically now. Let's interact with more research teams, universities, and all of the research centers to look for different topology to be scalable and scale with the high power and low processor node in this little card. Start seeing more and more modular approach to fit in this tiny area. Left and right, we have about 80 millimeter width is very tiny, maybe up to 10 millimeter. So definitely to increase the current density, when scalable solution, modular approach is gonna be very, very good solution. We start seeing modular approaches start coming to the market now, which is fantastic. But we compromise something with this, with the modular approach that we start seeing in the market. We compromise the efficiency. So modular approach is the right thing to do. We need a new magnetic implementation or design approach, and instead of discrete, we need to look for a different integration of the inductor or the magnetic within this modular approach. The current density, as I mentioned, we start seeing more and more modular approach to improve the current density. I start hearing people say, oh, we can push 40 amp and 50 amp per phase. Yes, I start seeing that, but with compromisation in the efficiency. We cannot do that. Again, we have also target or to deliver certain performance. So every time we deliver more current and compromise the efficiency, we compromise the performance. So that's loss of power. We cannot deliver more current with 20 or 30% loss in efficiency because basically it's not a useful solution. So we need to do both. We need to improve the current density and we need also improve the efficiency. Current density, we can say, okay, what about delivering 2 amp per millimeter square? People say, oh, it's available today. Yes, it's available today with horrible efficiency. Let's deliver 2 amp per millimeter square and high efficiency. People say, okay, we need to switch at higher switching frequency to improve the magnetic, but magnetic also is not only the only factor, but also the semiconductor material. To switch at higher switching frequency, we need to look for a new semiconductor material. Why not look for wide bandgap material that allowing us to switch at higher switching frequency? Always, silicon is impacting the switching losses when we go to 1 and 2 and 3 megahertz. Okay, let's look for a different semiconductor material, wide bandgap, enabling higher switching frequency. Bulky, magnetic. Let's look also for the capacitors. Or during low transient, now when the current starts increasing, the load step will be much, much, much higher. So we cannot keep adding capacitor to handle the low transient. Okay, let's look for coupling, magnetic coupling or electrical coupling to improve the low transient, to improve also the capacitor required for low transient. As I mentioned, let's look for topology with direct conversion from 48. That could be transformer topology. Why not transformer topology? Magnetic is another big challenge, yes, but if you start looking for advanced technology to use a transformer-based topology, it's doable. I start seeing a lot of research in this area, and with the cooperation with the industry, we can take research ideas and convert this into products. Thermal resistance is another big challenge. People say, okay, I can deliver 50 amp and 60 amp per phase, and the efficiency is horrible. A lot of dissipation heat within the components in a very small area, but also coming with a small thermal resistance, with high temperature coming to the module and the liquid coming to the SoC first and then go to the power components at the end. The temperature is getting hotter. And with thermal resistance, high thermal resistance with a lot of power dissipation per component, thermal teams say, okay, we cannot cool it. Yes, you can deliver high current density, but we cannot cool it. And many times thermal team shuts down solutions because they cannot cool it, because the thermal resistance is very high. Vendors and power semiconductors say, oh, we deliver to you the power density you're looking for, but I cannot cool it. So thermal is a huge factor. Thermal resistance is a big, big, big factor. It's a challenge in everywhere, mechanically, thermally, electrically, everywhere it's a challenge to us. Second message is for the data center facilities. Okay, help us also. Okay, don't ask for higher power without narrowing the input voltage range. We heard early in this morning, early this afternoon, the OpenRack V3, they are asking for narrower range, 48 to 51. There are still certain data center facilities cannot adapt this narrower range. We need the whole community to work together. If you would like to deliver higher power with high performance, let's work together as a community also to narrow this input voltage range. And instead of 40 to 60, let's make it 48 to 51, for example. Why not even regulated single voltage, regulated 48 volt, plus minus 10%. So let's look for the whole system end to end. All of us work together to deliver end-to-end efficient system. It is going to help all of us. When we have single input voltage or a narrower range, the power delivery will be more optimized. It can shrink. The magnetic can shrink if we design for a narrower range or a single input voltage instead of wide input voltage. Thermal. Chris did talk earlier that practical. Let's make the inlet temperature about 30 degrees C. Yes, that will help a lot. Designing for higher power at W4 or W plus 45 degrees C or 48 degrees, it's impractical at all. So definitely we need a lower temperature to enable a more efficient power solution. So let's put everything together. The OAM form factor has very limited space for the VR. Basically, the processor will take most of the space, and then mechanical, connector. What left over is just for power, like as usually the last thing for power. Mechanical, thermal, input voltage range, adding difficulties to the design. And it's easy to say that the VR technology is not progressing as fast as the processor node. The VR is still way behind the processor node. The processor node moving much faster than the VR technologies available. Now, as I mentioned, power community needs to innovate at all levels. Architecture, implementation, magnetic material, magnetic implementation, semiconductor material. At all levels, it's a time to innovate. This is reminding me of a time when we moved from 5 to 12. It was the same thing. We came with the 2 to 1, 12 to 6, and then we take buck converter as a second stage. And we are in the second renovation now. We're going from 12 to 48. Many design take a first stage, converting 48 to 12 and take buck again. I think it's time to change that. It's time to look very comprehensively to the problem. Again, our friends at the data center facilities, please help us also getting end-to-end improved efficiency. That concludes our presentation for today. It's a lot of challenges, a lot of opportunity to improve things and getting things much better. Okay, thank you, and willing to take any question?
Thank you. Any questions for the team here?
Okay, feel free.
First, the assembly, because you have now 2 connectors and also many components, to make sure that this will be at least can be assembled with misalignment can be happen between the connector. In addition, also to survive thermal cycle, power cycle, drop test. Can you comment that and about this challenge?
I'm not expert in reliability and assembly, but one thing that, and thanks for Sung and Anthony and the rest of the team, that now you see the OAM has power entry from 2 sides instead of 1 side. That was also a big challenge for thermal when it was the entry of the power from 1 side, and adding challenge, and now bringing power from 2 sides help the connector. Yes, too many components on single card is adding challenge. Definitely, I agree with you I'm going to defer this question to more people who are familiar with reliability better than me. I'm a power person.
We see also signal integrity an issue here, especially going beyond 112G and using anything you put it in it, even from mechanically. For example, if mechanically I use edge bonding, I can impact your signal integrity. You don't have any more air for crosstalk.
We are facing big challenge now in the layout. Just laying out the high-speed signals with the power, it's adding complexity that how both of them interacting with each other. The noise coupling between of them, it's a big challenge. So definitely we spend a lot of time. My friend here, maybe Son, can add more about the high-speed signal, but it's adding a lot of difficulties. I don't know, Alan, if you'd like to add anything.
That's exactly right. We're sharing the same PCB, and you can only do so much. When the bit rate is hitting 112 and PAM4, and they're talking higher PCIe Gen 6, right? So, yeah, it's a challenge. It's the same form factor. I think that's the challenging thing. As all these power and speed goes up, the module isn't getting any bigger. It's the same module. So we're going to be faced with many challenges that need a lot of different people to put their heads together to figure this out.
Yeah, so first of all, thanks to both of you for the presentation and for the call to action. It's good to hear that you are ready for a change and willing to accept something more exotic.
Yes.
My question is, how soon do you expect to need this kind of innovation? How much room do you have to use the existing solution at scale, just as far as timeline, right? To have an idea when is this needed, right?
Yesterday.
As all things technical.
No, it's happening already. The OAM is 700 watts. And the processor node is going lower voltage more and more. So definitely we need this to happen as soon as possible. Definitely it has to happen.
Okay, thank you.
Thank you.
So you're talking about a lot of challenges and all, and sorry if I'm a little bit disconnected, but is the Ponte Vecchio on the OAM module, do you have a target date for that? Or is that already, what's your roadmap, like time frame?
Again, OAM, all of the presentation today about OAM itself. So as Sarosh presented, Ponte Vecchio, one of the form factor is OAM. Ponte Vecchio is implemented in OAM.
It is committed, but can you comment on the release date of that?
Yeah, we're targeting release with the software stack in 2022, next year.
Okay. Thank you.
Thank you.